about today is the cohomology and partial quotients, in particular in combinatorial terms. But obviously, I will talk a bit more about what that means a bit later. And of course, I must mention that this is work with Shinfu, so we have already met, and also Yelena, who will be joining us. So before we can talk about partial quotients, we really should start the story a little bit earlier, maybe with moment angle manifolds. So let's say, let P be a simple polytope. And so by polytope, I mean, polygons, polyhedra, and higher dimensions. And the word simple just means that for an n-dimensional polytope, at any vertex, we have n facets meeting at that point, or n edges, whatever. The only reason we want this is so that if we take the boundary of the dual of the polytope, we get a simplicial complex. So this is just put this in a nice setting for working with simplicial complexes. So I have a simple polytope with m facets. So these are the codimension 1 faces. Then we can find a moment angle manifold for this. Which I will write as a ZP. And it looks like our normal definition, right? So we'll take a union over all possible faces. Let's say F. Which is an intersection of a number of facets. Maybe I should give the facets names. Maybe I'll say F1 up to M. Then I take the union of product of M spaces Y1 to Ym, where these Yi are either D2, so yeah, polyhedral product with D2S1, I guess, where we take a D2 if F is inside the Fi facets, and an S1 if F is not inside the F facet. But this is exactly the normal definition, right? I'm just using polytopes instead. And the reason that we use polytopes is that we end up getting a manifold each time. So it just gives us a little bit extra structure than if we're working with a normal moment angle complex. So yeah, classic, simplest example, which we will come back to many times during this talk, is when P is just an interval. So the facets, there are only just 2 facets, F1, F2. Then ZP is going to be our usual D2 cross S1 union S1 cross D2, or in other words, our boundary over D4, S3. Then PZP admit action of a TM torus. So ZP a TM action that works component-wise, right? By this, like each of the S1s in this product of M S1s can act on the S1s and D2s in this product. But we can consider a subgroup of this TM. So let's say let H be a subgroup of TM. Then we have a quotient map. So TM going to TM quotiented by H. And then this will induce map, let's see, induces a map lambda from H1 TM, so the first homology of TM, the first homology of TM quotiented by H, which looks like this is given by an integral matrix, right? Oops, wrong arrow. Yeah, integral matrix. Well, the point of me introducing this action is because really we want to talk about what this partial quotient is. So we define the partial quotient. Is ZP quotiented by the kernel of lambda. Okay, before we can talk about the cohomology of these things, we should first play with some, at least have an idea of what examples we can think of. So first of all, if lambda was just normal identity matrix and m by m identity matrix, then ZP should just be, sorry, the partial quotient should really be the normal moment angle complex. But in addition, we can do so much more. A second example, we can say if lambda was a 1, 0, 0, 1, 1, 1, and P, let's say, is a triangle, then it so happens that ZP quotiented up by kernel of lambda should give us a CP2. And in general, you can get CPN if you play with any simplex and ends.
Excuse me, I'm slightly confused. So we're looking at an action of TM on the before, but care of lambda lives inside the H1 of TM? Or what does it mean to mod out ZP by the kernel of lambda?
P over H, not kernel H.
The subtorus corresponds to the kernel.
P over H.
Is a subgroup of TL.
Oh,
H and H equals to the kernel of exponential. So which is the quotient map. So yeah, it's that P over H.
okay, okay. Ooh. Apparently it should be ZP over H. Where did the question come from? Oh, hi. Yeah, I guess it should be over H here. But we tend to write over kernel lambda.
Yeah, because that means the quotient map of that.
Ah, I see. Right. Yes, I guess it's a notational thing from my point of view. Yeah, anyway, so I wanted to talk about we get our moment angle manifold case, so this is good. And also we get our like way larger class of spaces out of this partial quotient construction. Yeah. So then this isn't just, by the way, like an arbitrary way of quotienting out some part of a moment angle manifold or complex. These spaces, these partial quotients, actually crop up in they are the topological analog of toric varieties. So they do crop up in algebraic geometry as well. So yeah, we really want to talk about the cohomology of these spaces. The motivation for talking about the cohomology of these things comes from the cohomology of moment angle manifolds. Cohomology. Where in this case we have the rather well-known results. I'm going to just concatenate a few different results here, but this is the result from Buchstaber Parnov, Franz, Buskakov, and Hopstead, which says that the cohomology of the moment angle complex, moment angle manifold, I'm just translating everything into manifold language, is isomorphic to a Tor algebra where this KP here, this should be that face ring or the Stanley-Reisner ring. That's quite familiar. The point is, working explicitly with the Tor algebra can be kind of tricky. We're trying to find explicit generators and explicit ways to see the cohomology of the moment angle complex. So we also have something that's called Hochsch's theorem, which says that the cohomology, or this Tor algebra, I guess, or this cohomology of a moment angle manifold is actually can be seen as a direct sum over J in M. We take the reduced cohomology of a PJ, but by PJ here, I guess I mean like a P restricted to the J facet. So when I'm talking about in combinatorial terms, this is exactly what we mean. The idea of this is really that the cohomology of ZP is somehow encoded in P. Right, this is I should also mention these are not just isomorphisms as algebras, these are as modules, they're actually isomorphisms of as algebras. So we really have the product here. And in fact, the cut product on ZP kind of comes from the product of spheres of polytopes. So let's say it comes from the fact that if we take a ZP1 cross P2, then this should give us a ZP1 cross ZP2. It's like, so the product on moment angle manifolds is kind of induced by this product. So for example, if P1 was our example from earlier, this interval, we knew that ZP1 should be an S3. But if we take another copy of this, so maybe P2 is also an interval, so we get another copy of an S3 here. Then P1 plus P2 gives us a square, and actually the moment angle manifold for this should be an S3 cross S3, as we should expect from seeing this kind of product structure. And also, if you've been to any of my previous talks, you will probably know it's not just cut products, right, that we can encode on the combinatorics in P, but also higher products like massive products and things like this. There's really a surprising amount of cohomology that gets encoded in P. So the goal was to think about, can we do this, something similar, something analogous when it comes to the partial quotient? Let's say cohomology of so if we're looking at the partial cohomology of partial quotients, there are some existing results. For example, there is a theorem by Franz that says if it should be H somehow. If H acts freely on ZP, which just means that we don't end up getting an orbifold when we take the quotient, then it's a condition on the some determinants in some parts of the matrix lambda. Then the cohomology of the partial quotient, which, yeah, I guess we write like this, should be equal to, well, is equal to the 4 over cohomology of B. I don't remember. TM H KPK. So the idea is that it's basically the same as the Buchstabe Panoff result. Just maybe some more of this action, this lambda is kind of contained here, but kind of similar. This is a isomorphism of algebras, but there is a twisted product. So it's not the standard product that you might expect on the taut algebra. It's with So as I said already, this isn't necessarily the easiest thing to work with when we want to find explicit generators and for the cohomology. But he did also show that the cohomology of the partial quotients is isomorphic, but this time only as modules. To an object equal B, in this case it would be P, and single quotients all the way through. So this is an object, it does contain a lot of the combinatorics of P as well. But unfortunately, we do not know a product here. So no cut product. So we're getting part of the way to the story, but not quite. This is where our approaches come. We really think, the idea should be that the cohomology of these partial quotients should be encoded in not just P, because that doesn't contain enough information, right? We really need to hold the lambda as well. So it should be somehow encoded in both P and lambda. So we kind of want to have some combinatorial object that carries information from both of these two things at the same time. And in particular, ideally, we want to get to where we could see the cut product structure. So our result is that, let's say that lambda be an integral matrix. Let's see that, let's just say represents a reaction. So just the same condition as Francis one, but also we want to say with at most two non-zero entries. In each column. Then in this case, the cohomology of the partial quotient is equal to a direct sum over J such that I guess in J and an I. I and J such that I plus J is equal to L of H L. I'm adding a subscript W. I'll come back to this. P lambda J. Oh, sorry, I should say yes. Then there's this a sequence of vectors. P lambda J. So the sequence of complexes indexed by this J, and we want to take actually a weighted cohomology. So this is weighted cohomology, and in each case, this is a complex that not just has that combinatorics of P, but also has a weighting on it that comes from this lambda. So I think it's probably easiest to talk about this in terms of an example.
Does the weighting have something to do with I? Like do something over I?
Oh, hello. Good show. When I wrote L, this should be a shorter L, and then with a dot. Thank you. Yeah, let's talk about an example. So let's say we have in a case where P is a square with 4 facets, right? 1, 2, 3, 4. And lambda is a matrix 1, 2, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1. Fairly arbitrarily chosen, to be honest. The idea is it's not an identity matrix. We should be able to spot that much, but it is quite close to it. The key difference is, we have 1 row less. So that's why the cohomology should be different. It's what we'd expect from an identity matrix. Then in this case, if we were to look at the first complex in the sequence, it should look something a little like this. So we're going to have 3 copies of the square. 1, 2. But the idea is, okay, so we have 3 copies of the square for one for each row. But the fact that this column has 2 non-zero entries in it means that I want to identify them along a particular face. And then the fact that none of the rest of them columns have 2 rows in them means that I want to identify a corresponding face to the identity. So somehow to a point. So I don't know, maybe somehow I identify this edge to a point, and I also end up identifying these 2 edges also to the point. Okay, we're still not quite done. I mean, we still need the weight, right? So far, we haven't accounted for what values that there are in lambda. So yeah, we want to assign a weight. So let's say for any L-1 face, say F of this complex, and an L face capital F, but that little f is contained in big F. We define a weight W F capital F. So somehow we're not just giving a weight to each face, but it's a weight to a pair of faces, that sort of F with respect to the larger capital F in some way. For facets, the weight comes directly from lambda. So here I would say that maybe if I give some things some names, let's call this edge A, this edge B, this edge C. And let's say that the 2 simplices, or like the square inside, are labeled P1, P2. Then the weight on A, P1 should come from lambda. So this will end up being a -2, representing this 2 here. And then the weight on A, P2 should be a 1 coming from the 1 in the first column. For anything that doesn't kind of get affected by lambda, we should have just the sort of standard weight of just 1. So let's say for B, P1, And also, sorry, I meant CP1 and BP2. These should just have the normal weight 1. And then for anything that isn't a facet, these should be defined inductively. So in other words, if we look at the weight on that vertex in between them, let's say this vertex is a vertex B. Then we want to assign a weight, let's say VA, that comes from the lowest common multiple of the weights A, P1, and CP1, divided by the weight on AP1, times lowest common multiple of AP2 and BP2, divided by AP2. That is somehow, we've got the weights coming from lambda directly. Maybe if I draw them on here, so maybe I have a -2 and a 1 there and a 1 there. Then when I take the weight on this, let's say A, I want to take the lowest common multiple of everything that happens in P1 and the lowest common multiple of everything that happens in P2, and then sort of normalize these lowest common multiples by the weight that's on A itself. And then, yeah, maybe it is possible to check, yeah, that if you do the similar thing for the other edges, so not just VA, but VB and VC, then we should get the weighted differential of V is equal to 0. Where I should say the differential for this, I guess we have a weighted cochain complex that looks exactly like the usual cochain complex, the cubical cochain complex. Right, looks like a cubical complex. So we should just have normal vertices, edges, and faces. But it's the weighted differential that makes the difference. So with dw of face is equal to sum over all larger faces, say F, with F inside capital F, and then dimension of F, capital F is equal to dimension of F plus 1. Then we take our weight of F, little f with the capital F. Then let's say this I shouldn't put I. For I little f in C, let's say L minus 1, P lambda 1. So F really is an L minus 1 face of this complex. Then this differential is exactly the usual differential. This epsilon is just the sign that's induced by the orientation. So nothing special happening here. If we remove the weight, or rather just set the weight as 1, which should be the case for the moment angle complex, where we have just identity matrix, then this is exactly the usual differential. So everything looks basically the same. It's just we have this extra weighting on each of our bases. Then we're able to define this weighted cohomology of these complexes. So this looks really analogous to the Hochster theorem, right? This is it looks basically the same. The only difference is really this weight and what this complex is. Otherwise, it's very, very similar. Of course, we haven't talked about the product. So the product is still a work in progress. This is still definitely our next step. But somehow the idea for this, I don't have a ton of space. Maybe if I just have a little extra place. The idea is that if I look at the next p lambdas, so p lambda 2, this should look like, well, it should have something in it that looks a bit like this, where have these 3 edges are identified to a point, and also this top one is, and then p lambda 3 should end up looking like a square, but with all of the edges around it identified to a point. And so somehow these classes kind of come from the fact that this, if we identify these 2 points, 2 edges to a point, we kind of get something that looks a bit like an S1. This one also looks a little bit like an S1, and this one ends up looking like an S2, right? If I take all of the boundary of a disk and identify it to a point, I get S2 here. But also the product kind of shows up, you know, we know from before we're looking for a product of 2 intervals to some extent. So the idea is that somehow these missing edges kind of look like an interval here. And these missing edges look kind of like an interval here. And then this gets represented in the sort of top dimension by the product of these pairs of missing edges. So somehow there is still the essence of why we should have a product from the moment angle complex, moment angle manifold, still resembles something in these pictures. But as I said, it's still a work in progress and definitely our next step. So maybe you'll hear more about it sometime in the future. Thanks.